Okay, hello again, ladies and gentlemen. We're going to move on to the next phase of proofs. Okay, we've covered pretty much the five basic methods of proving triangles congruent. Okay, so I'm just going to refresh your memory of what those were. Okay, we started out with side, angle, side. Okay, and then I went on to side, side, side. Okay, and then the next day I introduced two more, angle, side, angle, and angle, angle, side. Okay, and then the last one that we did was hypotenuse, leg. Okay, so those are the five possible ways of proving a triangle or two triangles congruent to each other. Okay, now one you might notice is missing here, okay, is side, side, angle. Okay, side, side angle is not a choice here. Okay, and here I'm going to explain why. Okay, so I'm going to draw a triangle that looks like this. Okay, um, triangle looks like this. Um, okay, so I'm going to draw a triangle that looks like this. Okay, and over next to it, I'm going to draw a triangle with this same angle. Okay, so here's that same angle. Okay, this same side, okay, so we'll make that about the same length. There you go. Okay, and now I can draw another triangle with this same length, but it's not the same triangle. Okay, if I were to swing this side this way, okay, and draw this in this way, okay, I would get a triangle that looked like this. Okay, so I would have angle, side, side, congruent to angle, side, side, but I don't have the same triangle. Okay, so for that reason, okay, angle, side, side, okay, is not a method that we can use. Okay, you cannot use, okay, you cannot use, okay, angle, side, side as a method for proving triangles congruent to each other. Okay? You cannot use that one. Okay? Unless you want to look like one of those, don't try it. Okay? Do not try to use angle, side, side to prove two triangles are congruent to each other. This is something called the ambiguous case, okay, where you've got an angle and two sides congruent to an angle and two sides, but you can form two completely different triangles from them. Okay, you'll learn more about that in Algebra 2 when you do a little bit more trig. Okay, but for now, do not try and use angle, side, side. Okay, so that's that. All right, so today we're going to talk a little bit about using some of these other postulates that we talked about on the very first day. Okay, you might remember this sheet. Okay, we already used reflexive quite a bit. Okay, now down here, about halfway down, we see these three: partition, addition, and subtraction, and those are the ones we're going to talk about today. Okay, so these are already on the notes sheet. Okay, but I just wanted to point them out. These are the things that we saw on that very first day. So here they are. Okay, partition postulate. A whole is equal to the sum of all its parts. Okay, so I'm going to talk about that when we get to it. Okay, addition postulate. You may recall what I said when we did this was you need two sets of equal quantities, A equals B and C equals D. And the example I used was 3 equals 3 and 5 equals 5. Okay, and if I take one from each of those groups and I add them, the sums are going to be the same. A plus C equals B plus D. That's the same thing as saying, well, 3 plus 5 equals 3 plus 5. Okay, seems like a silly postulate, but we're going to be using that in the next example to piece together the parts that we need to prove the triangles congruent to each other. Okay, and there's this also the subtraction postulate, which if I subtract, again, I need two sets of equal quantities in order to apply it. Okay, again, 3 equals 3, 5 equals 5. doesn't 3 minus 5 also equal 3 minus 5? If I take one from each set and subtract them, the differences are the same. Okay, so that's essentially the same concept that we're going to be using when we use these in proofs. Okay, so here's our first example. Okay, CD is a median to AB. Remember what that means. CD is a median, means it goes from the vertex to the midpoint of the opposite side. So that means I can mark that AD is congruent to BD. Okay, now look what else I'm given. I'm given CE is congruent to CF. So this little piece is congruent to that little piece. Okay, that's not the entire side of the triangle. Okay, so I can't just say, well, that's my other side. Okay, and I also have EA is congruent to FB. That means this piece is congruent to that piece. Okay, again, not an entire side, but it is part of a side. Okay, and what I have here are the ingredients for the addition postulate. I've got two sets of equal quantities. Okay, if I add one from each, their sums must be the same. Their sums must be equal. So if I add CE plus EA, that's going to equal CF plus FB. And that's going to allow me to say that this whole thing, CA, is congruent to CB. Okay, and then we can go ahead and prove those two triangles congruent to each other. Okay, so that's what I'm going to show you, and I'm going to show you the steps for using the addition postulate. And it's going to go together with two other postulates. It's also going to go together with the substitution postulate and also the partition postulate. Okay. Okay, so here we go. All right, so my first statement, CD is a median to AB. Okay. Gonna number that. 1. Okay, and over here, I'm going to say 1. That's given. Okay, from that, okay, I can then say the first thing that I marked was AD. AD is congruent to BD. And that is by definition of median. The definition of median says that CD goes to the midpoint of AB, meaning those two segments are equal. So we can say definition of median. Okay, so that's that side. All right, now I'm going to add in those other two givens. Okay, that's CE is congruent to CF, and I'm going to say EA is congruent to FB. Okay, I need those introduced into the proof because in order to use addition, I need two sets of equal quantities to add. Okay, now I have two sets of equal quantities. All right, so what that allows me to do is add, just like I did 3 plus 5 equals 3 plus 5, I can add them. I can say CE plus EA equals CF plus FB. Okay, I took one from each of those and I added them together. Okay, and the sums are equal. So I can say this is the addition postulate. Okay, addition postulate. Okay, now I'm going to use the next postulate, the one actually that's listed first up here. Okay, which is the partition postulate. A whole is equal to the sum of its parts. Okay, so this will be important in this proof down here. A whole is equal to the sum of its parts. So CA equals the sum of its parts. So I'm going to write that CA equals CE plus EA. Okay, and I'm also going to write on the other side, again, I can combine the two. They're similar statements. and they have the same reason. So I can write that CB equals CF plus FB. Okay. Now the reason I can say both of those things, okay, now is 5. That's the partition postulate. Okay, that is the whole CA equals the sum of its parts, CE plus EA. And this whole CB equals the sum of its parts, CF plus FB. Okay, so that's how that partition postulate works. Okay, and now the third step, which goes, all three of these, 4, 5, and 6 go together. Okay, I'm going to now use what's called the substitution postulate. Okay, I don't have that one on this sheet. Okay, but if we look back at the postulates and theorems, okay, it was here. Okay, the substitution postulate is here. Okay, a quantity can be substituted for its equal in any expression. A quantity can be substituted for its equal in any expression. Okay, so I'm going to go back to here, and what I'm going to do is I'm going to take CA. Let me circle it here. CA, and I'm going to substitute for its equal into this expression. Okay, the one above it, and that's going to become down here. CA equals, okay, and I'm going to take CB, which is here, and I'm going to substitute it for its equal in the same expression. So now I'm getting CA equals CB. Okay, so I took those two sums and I substituted for their equals. Okay, since CA equals CE plus EA, I can put in CA. Since CB equals CF plus FB, I can put in CB, and I get statement 6. Okay, and that is the substitution. I spell that right? Substitution postulate. Okay, and that is how I get CA congruent to CB in this proof using the addition postulate. Okay, those 3 steps go together. Okay, these 3 steps go together in that order using these 3 reasons in that order. Okay, so let's finish this one up. I could do CD as congruent to CD and be done. I could do the reflexive postulate and use side, side, side. Okay, but what I'd like to do instead, okay, since I've got CA congruent to CB, I'm going to say that angle A is congruent to angle B. Okay, angle A is congruent to angle B. Okay, because, and I use this in the hypotenuse leg proofs. Okay, because in a triangle, the angles opposite congruent sides are congruent. Okay, since AC equals BC, that's an isosceles triangle, and A and B are the base angles of that isosceles triangle. Okay, so in a triangle, the angles opposite congruent sides are congruent. Okay, so now I can say that 8 triangle ACD is congruent to triangle ABC, BCD. Okay, and the reason that I'm going to use, okay, since I use those angles, is now 8, that is side angle side, congruent to side angle side. Okay, again, I could have used side, side, side by throwing in CD as reflexive. Okay, there can be more than one way of solving any one of these proofs. Okay, as long as you can support it with reasons, statements, and reasons, it's okay. Okay, so in this case, I chose to do side angle side just to remind you of that that reason in number 7. In a triangle, the angles opposite congruent sides are congruent. Okay, so that's that one. But the basic meat of this one is steps 4, 5, and 6, how we're going to use addition, partition, and substitution. Okay?